morning, dear students. I myself Shyama Prasad, head of the Department of Electronics, Alvas Pre-University College, Modubidre. Today, we are going to study the theory of operational amplifier, simply abbreviated as op-amp. In your textbook, it is the chapter number 5. The marks allotted for this chapter is 11 marks. It is one of the important chapter for annual examination. Let us study the theory of operational amplifier. Now, what is operational amplifier? The operational amplifier is one of the versatile amplifier. Versatile in the sense, it can be used to amplify both alternating current as well as the direct current. The op-amp is a versatile amplifier. It is a direct coupled amplifier. In the case of the CE amplifier, the CB amplifier and the CC amplifier, it uses these amplifiers use capacitors. The capacitor blocks DC and allows AC to pass through. Therefore, the basic common emitter amplifier, common base amplifier, common collector amplifiers cannot be used to amplify the direct currents. But operational amplifier is one of the versatile amplifier which can be used to amplify both alternating current as well as the direct current. So, the operational amplifier is a versatile direct coupled high gain amplifier. It provides very high voltage gain, and it consists of what is known as a differential amplifier. A differential amplifier is the one which amplifies the difference between the two input signals. So, the op-amp consists of few differential amplifier stages. In addition to that, it consists of what is known as a level translator and an output stage. Now, what is op-amp or operational amplifier? An operational amplifier is a high gain direct coupled versatile amplifier, usually consisting of one or more differential amplifiers along with a level translator and an output stage. The op-amp is used for number of applications. The op-amp was originally designed to perform the basic mathematical operations such as addition, subtraction, multiplication and division. It can also be used to solve simultaneous equations. The other applications like op-amp integrator, op-amp differentiators are the common applications of the op-amp. The important applications of the op-amp are, one is the active filters. Already you have studied two types of filters like low pass filter and high pass filters. So, the op-amp can be used as active filters. It can be used as an amplifier, analog to digital converters, digital to analog converters, wave shaping circuits, comparators, oscillators, etc. These are the applications of the op-amp. These days, op-amp is available in the form of the integrated circuit. One of the commonly used op-amp IC 741. We are going to study the theory of IC 741. It is one of the IC which is available in the form of dual inline package, monolithic dual inline package. The IC consists of 8 pins, 4 pins on one side and 4 pins on other side. Let us study the block diagram of the general purpose operational amplifier. The operational amplifier, let us study the block diagram. This is a block diagram of the general purpose operational amplifier. The operational amplifier consists of two inputs. These inputs are called the inverting input and the non-inverting inputs. The inverting input is marked as V2 and the non-inverting input is marked as V1. These inputs are applied to a circuit known as the differential amplifier. The differential amplifier amplifies the difference between the two input signals. Now, these inputs are applied to the first stage, which is known as the input stage. The input stage is a differential amplifier This differential amplifier stage provides very high input impedance and very low output impedance. The input stage also provides very high voltage gain. The output of the input stage is connected to a circuit known as the intermediate stage, or it is also called the gain stage. The intermediate stage also provides very high voltage gain. Now, the first two stages provide very high voltage gain. These two stages increase the input impedance of the amplifier. Now, the output of the intermediate stage is connected to what is known as a level translator, or it is also called the level shifting circuit. Now, since the operational amplifier amplifies both direct currents and also the alternating currents, the output of the intermediate stage is usually well above the ground potential. This is because the operational amplifier does not use capacitors. So, the output signal may be well above the ground potential, or it may be well below the ground potential depending on the DC polarity. Therefore, the output measured across the intermediate stage may be well above the ground potential. So, in order to bring down the output of the intermediate stage to 0, we use what is known as the level shifting stage. The level shifting stage is basically an emitter follower. This emitter follower stage mainly used to reduce the output DC of the intermediate stage downward to 0 with respect to ground. The output of the level shifting stage is connected to an output stage. The output stage is a power amplifier. Class B push pull power amplifier is used. This class B push pull power amplifier stage increases the current supplying capability of the op amp. That means the output stage increases the current supplying capability of the op amp, which in turn reduces the output impedance of the amplifier. Now, the last two stages, that is the level shifting stage and the output stage, increases the current supplying capability of the op amp. That means these two stages amplify the current. The first two stages will amplify the voltage, which in turn increases the overall power gain of the signal. So, you know the power formula for power is equal to product of voltage and current. Power gain is nothing but product of voltage gain and current gain. Therefore, the first two stages will provide very high voltage gain. The next two stages will provide very high current gain. Now, the first two stages will also establish the input impedance of the amplifier. Normally, the input impedance of the amplifier is very high and output impedance of the amplifier is very low in the case of the op amp. Now, there are two inputs. These inputs are marked as the inverting input and the non-inverting inputs. Now, why do we call these inputs as inverting and non-inverting inputs? Now, consider the non-inverting input. If the input signal is applied to the non-inverting input terminal of the op amp, then output signal will be in phase with the input signal. That means, when we apply the positive half cycle of the input signal to the non-inverting input, then output signal will be the positive half cycle. And when we apply the negative half cycle of the input signal to the non-inverting input, then output signal will also be negative half cycle. So, the non-inverting input V1 alone produces an in-phase output signal. For this reason, this input is called the non-inverting input. The next input is the inverting input. If the input signal is applied to the inverting input terminal alone, then the output signal will be out of phase with the input signal. That means, when the positive half cycle of the input signal is applied to the inverting input terminal, then output signal will be the negative half cycle. When we apply the negative half cycle of the input signal to the inverting input, then the output signal will be the positive half cycle. So, when we apply the input signal to the inverting input terminal alone, then output signal and the input signal differ by a phase angle of 180 degree. So, now these inputs are marked as V1 and V2. The non-inverting input is usually marked as V1 and the inverting input is usually marked as V2. Now, let us study the circuit symbol of the operational amplifier. Now, the symbol resembles a triangle. Here there is a triangle. This triangle indicates the direction of flow of current, direction of flow of signal, that is from the input to the output. This triangle indicates the direction of flow of signal, that is from the input to the output. The two inputs are inverting input and the non-inverting input. Now, here we have to connect two power supplies. These are called the dual power supplies. One is the plus VCC and other is the minus VE. This is the circuit symbol of the operational amplifier. Now, let us study one of the commonly used IC, that is OP-amp 741. It is the general purpose operational amplifier. This IC was invented in the year 1970 by a Fairchild Semiconductor company. The Fairchild Semiconductor company invented this IC. These Fairchild Semiconductor ICs usually have the starting letter mu A. Mu A indicates manufactured by the Fairchild Semiconductors. Now, let us study the different manufacturers of the operational amplifier ICs. The Fairchild Semiconductor ICs usually have the initials mu A. Mu A indicates manufactured by National Semiconductor. Now, the IC is mu A 741 and another is mu AF. It may have the initials like mu AF also. The IC number mu AF 741, and then some of the ICs have the initials LM. LM indicates manufactured by National Semiconductors. The National Semiconductor ICs have the initials LM. It may have initials like LH, LF and TBA. Now, LM 741, LM indicates manufactured by National Semiconductors. LH 0032 manufactured by National Semiconductors, LF 353, TBA 741. These are the ICs manufactured by National Semiconductor company. And next is the Motorola company. In these ICs, the initials may be MC or MFC. The MC 1741 and MFC 6040. These are the op-amp ICs manufactured by Motorola Semiconductors. And then RCA, another company, Radio Corporation America. In these ICs, the initial may be CA, CD, CA and CD. The IC number CA 3741 and CD 4007 manufactured by the Radio Corporation America, RCA company. And then Texas Instruments. Here initial may be SN. SN indicates manufactured by the Texas Instruments, SN 52741, and then Sprague company. In this ICs, the initials may be ULN, ULN 2595, ULS 2001 and ULX. These are the initials of Sprague company. ULN 2595, ULS 2001, the initials ULX. With ULX, initial ULX, there are number of ICs, ULX 200 to 215, around 15 ICs are there. So, these ICs will have the initials like ULN, ULS, ULX, etc. The next is the Intercell company. In this Intercell company, initial may be ICL, one of the IC, ICL 7611, and next is the Signetic Corporation. In case of Signetic Corporation ICs, the initial may be NE or SE, NE/SE. NE554, NE5554, these are the initials of the Signetics company, NE and SE. Then the another company Burr Brown, BB, the initial may be BB, but the starting letters may be OPA, OPA 353, it is also one of the op amp. Now, observe that there are different manufacturers of general purpose op amp, but then all 741 ICs will have the same pin configuration, but as the number of the IC differs, the pin configuration and also the power supply range will also vary. So, now let us study the power supply connections of the op amp. Op amp requires a dual power supply. Now, very easy to construct a dual power supply. Simply you need to use two batteries. Consider there are two batteries, say V1 and V2. Now, what you have to do? You have to connect the negative terminal of the first power supply to the positive terminal of the second power supply, which is called the common ground. Now, the positive terminal of the first power supply is connected to plus VCC of the op amp, and negative terminal of the second power supply is connected to the minus VE of the op amp. Here I am using two power supplies, two DC batteries with battery voltages 15 volts. I am considering two batteries, DC batteries with magnitude 15 volts. Now, negative terminal of the first power supply is connected to positive terminal of the second power supply, which is called the common ground. Now, the positive terminal of first power supply is connected to the plus VCC of the op amp. The negative terminal of the supply is connected to minus VE of the op amp. Let us study the pin configuration of the IC op amp 741. Here I am considering mu A741, the IC manufactured by Fairchild Semiconductors. Now, the op amp 741 is available in the form of monolithic dual inline package. That means there are total 8 pins. There are total 8 pins in the case of this 741 IC, 4 pins on one side and 4 pins on other side. If you observe the top view of the IC, you will observe a notch near one of the pin. This notch indicates it is the first pin of the IC. From this notch, you have to start counting the number of pins, 1, 2, 3, 4 on one side, and the other side 5, 6, 7, 8. There are total 8 pins on this IC. Now, the first pin and the fifth pin are marked as offset null. The first pin and the fifth pin are called offset null. The next pin is the inverting input, that is pin number 2. Pin number 3 is marked as non-inverting input. Pin number 4 is minus VEE. And pin number 6 is the output of the op amp. Usually the output signal is measured across this terminal. And next pin number 7 is plus VCC. Pin number 8 is no connection. It is not used in any electronic circuits. Let us observe the mu A741 IC. Here you can find the notch near one of the pin, which is the first pin of the IC. Here there are, you can see 4 pins over there, and there are 4 more pins on the other side of the IC. You just observe the top view. They have printed the number of the IC over here, mu A741. You can read the number on the IC. Now, there are total 3 packages available. The first one is the dual inline package. Dual inline package. Here the IC consists of 4 pins on one side and 4 pins on other side. The other one is called the metal can package. Here usually the IC consists of a metal cap along with 8 pins. On the other side there are total 8 pins. This is the metal can package. The number 741 is printed over there. And next one is the SOC package, small outline package. These ICs are usually used to solder on a PCB, but not used for practical purposes. In most of the embedded circuits, we use these printed circuit boards, we use these small outline packages. These are the three types of packages available. There is one more IC, that is AD827. It is one of the dual op amp. In a single IC, two op amps are available, so it is called dual op amp. The IC number is AD827. AD means manufactured by Analog Devices Company. Let us study the pin diagram of AD827 IC. This IC consists of total 8 pins. Now, the first pin is the output of the first op amp. There are two op amps in a single IC. It is a dual op amp. There are two op amps in a single IC. Now, for the first op amp, inputs are pin number 2 and pin number 3. Pin number 2 is the inverting input, pin number 3 is the non-inverting input of the first op amp, and pin number 1 is its output. The next op amp, that is the second op amp. For the second op amp, pin number 5 is the inverting input, pin number 5 is the non-inverting input, and pin number 6 is the inverting input. Pin number 7 is the output of the second op amp. Now, pin number 8 is connected to battery positive, that is plus VCC, and pin number 4 is connected to minus VEE. So, pin number 8 and pin number 4 are reserved for the power supply connections, that is plus VCC and minus VEE. So, this is the pin configuration of IC AD827, which is the dual op amp. The one more IC, that is LM324, it is the quad op amp. That means there are 4 op amps in a single IC package. Now, this is the first op amp, the second op amp, the third op amp, and the fourth op amp. Now, for the first op amp, pin number 2 and pin number 3 are the inputs. Pin number 2 is the inverting input, pin number 3 is the non-inverting input for the first op amp. Pin number 1 is the output of the first op amp. For the second op amp, pin number 5 is the non-inverting input, and pin number 6 is the inverting input, and pin number 7 is the output of the second op amp. Next is the third op amp. For the third op amp, pin number 10 is the non-inverting input, pin number 9 is the inverting input, and pin number 8 is the output of the third op amp. Consider the fourth op amp. For the fourth op amp, pin number 12 is the non-inverting input, and pin number 13 is the inverting input, and pin number 14 is the output of the fourth op amp. Now, pin number 4 and pin number 11 are used for battery connections. Pin number 4 is connected to battery positive, pin number 11 is connected to battery negative, or it is the ground connection. Usually LM324 is used operated with single power supply. Battery positive terminal is connected to pin number 4 and battery negative is connected to pin number 11 of the op amp. That is all about the op amp packages. One is MUA741, which consists of 8 pins, and then the AD827 IC, which consists of 2 op amps in a single IC package, and then the LM324, which consists of 4 op amps. This is the IC LM324. You can see the IC top view of the IC. The printed the number of the IC LM324. There are total 7 pins here on one side and 7 pins on the other side. There are total 14 pins. The operational amplifier basically consists of what is known as the differential amplifiers. What is differential amplifier? The differential amplifier basically an amplifier which amplifies the difference between the two input signals. The differential amplifier is a direct coupled amplifier. That means it does not use any capacitors. The input signal is directly connected to the base terminal of the transistor. Now, since it amplifies the difference between the two input signals, it is called the differential amplifier. The differential amplifiers are used to construct an operational amplifier. Let us study the block diagram of a differential amplifier. The differential amplifier may have one or two inputs and one or two outputs. Now, this consider there are two inputs V in 1 and V in 2, and there are two outputs VO1 and VO2. Now, depending on the number of inputs and number of outputs, there are 4 types of differential amplifier configurations. These differential amplifiers are classified based on the number of inputs and the number of outputs. If the input signals are applied to both input terminals of the differential amplifier, then it is called the dual input mode, or it is also called the double ended input, or it is also called the differential mode. In other words, if the input signal is applied to only one of the input terminal and the other input terminal is grounded, then it is called the single input mode. Now, if the output signals are measured across both output terminals, then it is called the balanced output configuration. If the output is measured across only one of the output terminal, then it is called the unbalanced output configuration. Now, let us classify the differential amplifiers. There are 4 types of differential amplifiers. One is called dual input balanced output differential amplifier. Dual input, that means the input signals are applied to both input terminals of the amplifier. Balanced output, the output signals are measured across both output terminals. So, dual input balanced output differential amplifier. The next configuration is dual input unbalanced output differential amplifier. In this configuration, the input signals are applied to both input terminals and output signal is measured across one of the output terminal with respect to ground. So, the name dual input unbalanced output. Input signals are applied to both input terminals, output signal is measured across only one of the output terminal. So, dual input unbalanced output differential amplifier. The next is the single input balanced output differential amplifier. Single input, that means input signal is applied to only one of the input terminal and the other input terminal is grounded. The output signal is measured across both output terminals. So, the configuration is called single input balanced output differential amplifier. The next configuration, that is single input unbalanced output differential amplifier. In this configuration, the input signal is applied to one of the input terminal and the other input terminal is connected to the ground. The output signal is measured across one of the output terminal with respect to ground. So, the name single input unbalanced output differential amplifier. Let us study the circuit diagram of the differential amplifiers. The differential amplifiers require two transistors which are exactly identical in all respects. It is very difficult to manufacture two transistors of exactly identical properties. Therefore, there exists some voltage which is known as the error voltage. The two transistors should have exactly identical properties. That means both transistors have same value of VBE and same value of beta, the current gain. Now, let us study the working of dual input balanced output differential amplifier. Now, what is dual input balanced output differential amplifier? In the case of dual input balanced output differential amplifier, there are two inputs. That means input signals are applied to both input terminals. The output signal is measured across both output terminals. So, the name dual input balanced output differential amplifier. Now, this is the circuit diagram of dual input balanced output differential amplifier. Here we are applying the input signal to base to emitter terminal of both transistors. The circuit consists of two transistors Q1 and Q2. The emitter terminals of the two transistors are joined together and a resistor Re is connected to it, connected to the emitter terminals of the transistor. Now, the other end of the resistor Ra is connected to the negative power supply, that is minus VEE. Now, it also consists of two collector resistors. One is RC1, which is the collector resistor connected to the transistor Q1, RC2, which is the collector resistor of transistor Q2. The other end of the collector resistors are connected to battery positive. Now, let us study the working of this amplifier. Here, the input signals are applied to both input terminals of the amplifier. So, the name dual input. Inputs are applied to both input terminals. Balanced output, that is output signals are measured across collector terminals of both transistors. So, the name dual input balanced output, two input terminals and two output terminals. Observe the block diagram of the dual input balanced output differential amplifier. Here input signals are applied to both input terminals. Output signal is measured across collector terminals of both transistors. So, dual input balanced output differential amplifier. The next configuration, that is dual input unbalanced output differential amplifier. In this configuration, input signals are applied to both input terminals. The output signal is measured across only one of the output terminal with respect to ground. So, the name dual input unbalanced output differential amplifier. Look at the circuit diagram of dual input balanced output differential amplifier. Here input signals are applied to both input terminals of the amplifier. The output signal is measured across collector terminal of one of the transistor with respect to ground. So, the name dual input balanced unbalanced output differential amplifier. So, there are two inputs but only one output terminal. So, dual input unbalanced output differential amplifier. Look at the block diagram of the dual input unbalanced output differential amplifier. Here input signals are applied to both input terminals and output signal is measured across collector terminal of one of the transistor with respect to ground. The next configuration, single input balanced output differential amplifier. In this configuration, input signal is applied to only one of the input terminal. The other input terminal is connected to the ground. So, the name single input balanced output. That means output signal is measured across collector terminals of both transistors. So, in single input balanced output configuration, now look at the circuit. Input is applied to, input signal is applied to base terminal of one of the transistor. The base terminal of the other transistor is grounded. The output signal is measured across collector terminals of both transistors. So, the name single input balanced output. Only one input signal, the other input signal is grounded. Output signal is measured across collector terminals of both transistors with respect to ground. Let us study the block diagram of the single input balanced output differential amplifier. In this case, the input signal is applied to one of the input terminal, other input terminal is connected to the ground. The output signal is measured across collector terminals of both transistors. The block diagram of single input balanced output differential amplifier. The next is the single input unbalanced output differential amplifier. Here the input signal is applied to one of the input terminal, the other input terminal is connected to the ground. The output signal is measured across collector terminal of one of the transistor with respect to ground. Let us study the circuit diagram of single input unbalanced output differential amplifier. Here the input signal is applied to only one of the input terminal. The other input terminal is connected to the ground. Output signal is measured across one of the output terminal with respect to the ground. So, the name single input unbalanced output differential amplifier. Observe the block diagram of the single input unbalanced output differential amplifier. Input signal is applied to one of the input terminal, other input terminal is connected to the ground. The output signal is measured across collector terminal of one of the transistor with respect to ground. Let us study the working of the dual input balanced output differential amplifier. As you know, the dual input balanced output differential amplifier consists of two input signals. Here we are going to apply the input signals to both input terminals. Since it is balanced output, output signals are measured across collector terminal of both transistors. Now, in order to analyze the working of the circuit, we use what is known as the superposition theorem. The superposition theorem states that in any linear bilateral network consisting of fixed sources and resistances, voltage across any specified terminal is equal to the algebraic voltage drops caused by individual voltage sources acting alone, while other sources are non-operative. So, in order to analyze the working of the circuit, we have to use what is known as the superposition theorem. According to superposition theorem, we have to determine the output voltage caused by individual voltage sources acting alone, while other sources are non-operative. That means you have to connect one of the input signal source, the other input signal source should be grounded, and then we will have to calculate the output voltage caused by V1 acting alone, while V2 is connected to the ground. So, next step is to connect the second voltage source and connect the first voltage source to the ground and determine the output voltage caused by the input voltage source V2 acting alone, while V1 is connected to the ground. Now, according to superposition theorem, total output voltage VO, that is equal to sum of VO1 plus VO2, where VO1 is the output voltage produced by V in 1 acting alone and VO2 is the output voltage caused by V in 2 acting alone, which is the effective output voltage. Now let us consider the input signal source V in 1 alone is connected. That means we have connected the second voltage source to the ground. Now observe the circuit. Let me connect the second voltage source to the ground. Only the first voltage source is connected to the base terminal of the transistor Q1. Now, since the input voltage source is connected to the base terminal of transistor Q1, the transistor Q1 will amplify the signal. Now, if you measure the voltage across collector terminal of the first transistor, then it will be out of phase. It differs by a phase angle of 180 degree. This is the property of common emitter amplifier. In the case of common emitter amplifier, input signal and output signal differ by a phase angle of 180 degree. So, when the input signal is applied to the base terminal of transistor Q1, the output signal measured across the collector terminal of the transistor Q1 differs by a phase angle of 180 degree. So, we are going to get the amplified signal across collector terminal of transistor Q1, but with a phase reversal. Let us consider the output signal is measured across emitter terminal of the transistor Q1. If the output signal is measured across emitter terminal of transistor Q1, it will be in phase with the input signal and has the same magnitude. You simply consider a pipe. Consider the water enters the pipe on one side, same water leaves the pipe on the other side, right. So, it is the property of the common collector amplifier. So, now here there is a direct path from the base to the emitter. Therefore, when we measure the output signal across the emitter terminal, it is nothing but the input voltage. We are going to get the same input voltage. So, we can say that voltage across the emitter terminal of the transistor Q1 is equal to the input voltage. Now, let us consider the remaining part of the circuit. Let me revert this circuit. You just observe this second part of the circuit. This circuit is actually the common base amplifier. Look at the circuit. There is a transistor Q2. You connected the second voltage source to the ground. Already we have grounded the second voltage source. The base terminal of second transistor is connected to the ground. So, now if you observe the second part of the circuit, it acts as common base amplifier. It consists of the emitter resistor RE. One end of the emitter resistor RE is connected to minus VA, and the other end of the collector resistor RC2, it is connected to positive of the battery. So, this transistor Q2 and associated circuit now acts as common base amplifier. Now, the input signal is applied to the emitter. Already we have studied that the voltage across the emitter terminal of transistor Q1 is nothing but the input voltage. So, now this input signal voltage which is applied to the emitter terminal of the transistor gets amplified, and now the amplified signal is available across the collector terminal of the second transistor. So, output signal measured across the collector terminal of the second transistor is in phase with the input signal. Now, note that when the input signal is applied to the base terminal of transistor Q1, the amplified signal measured across collector terminal of the first transistor is out of phase with the input signal. But when the output signal is measured across collector term of the second transistor, it will be in phase. When the output signal is measured across collector terminals of both transistor, then the output voltage VO, that is equal to VO1 minus of VO1. The total output voltage is usually calculated as the difference between the two voltages. You know, when you consider the positive half cycle, when you apply positive half cycle of the input signal, voltage across the collector terminal of first transistor will be negative half cycle. But if you measure the voltage across collector terminal of the second transistor, it will be positive half cycle. So, when we measure the voltage across two terminals, usually we say potential difference, that is voltage across A minus voltage across B. Voltage across collector terminal of first transistor is positive, voltage across second transistor is negative. Okay. Now, when we say the potential difference, we are measuring the difference in potential, that is voltage across A minus voltage across B. So, VO1 minus VO1. So, that is equal to 2 VO1. The output voltage is equal to twice amplified replica of the input signal. Now, why do we get twice amplified replica? The reason is very simple. Here there are two transistors. Both transistors amplify the signal. So, the amplified signal is available across the collector terminal of the two transistors. Now we have connected only the first voltage source and the second voltage source is connected to the ground. We will now connect, let us connect the second voltage source and the first voltage source is connected to the ground. Now, let us study the working of the circuit. Consider the second voltage source alone is connected. That means the first voltage source is connected to the ground. Now, when the input signal is applied to the base terminal of the second transistor, the transistor Q2 amplifies the signal. When we measure the voltage across collector terminal of the second transistor, it will be out of phase with the input signal. Now, let us observe the emitter terminal of the second transistor. What is the voltage across the emitter terminal of the second transistor? It is same as that of the input signal. Now, consider the remaining part of the circuit. Now, consider the transistor Q1 and associated circuit. This circuit acts as common base amplifier. Already we have connected the first voltage source to the ground. Look at the second part of the circuit, it acts as common base amplifier. The input signal is applied to the emitter terminal of the transistor Q1. The output signal is measured across collector term of the first transistor. So, amplified signal across collector term of the first transistor is in phase with the input signal. But when we measure the voltage across collector terminal of the second transistor, it will be out of phase. Now, when we measure the output voltage across collector terminal of both transistors, it will be twice amplified replica of the input signal. So, again we get 2VO1, twice amplified replica of the input signal. Consider both input signals are applied simultaneously. Now, what happens? When both input signals are applied to the base terminal of both transistors, both the signals with the VV11 and Vin2, both signals will flow through the same resistor. Moreover, these input signals are in opposite polarity. Now, both input signals will flow through the same resistor and have opposite polarity. Now, what happens? When both input signals are applied simultaneously, the actual input signal to the circuit becomes Vin1 minus Vin2. The difference between the two input signals get amplified. This is because both input signals will flow through the same emitter resistor Re, and these input signals get subtracted. So, the net input voltage to the amplifier now becomes Vin1 minus Vin2. The difference in the input between the two input signals get amplified and available across the collector terminal of the transistors. Consider the input signals are applied to both input terminals of the amplifier. When the input signals are applied to both input terminals, these input signals will flow through the same resistor. These input signals are in opposite polarity. Both input signals will flow through the same resistor. So, the net input voltage to the amplifier now becomes the difference between the two input signals. So, net input voltage Vin, that is equal to Vid, it is also called the input difference voltage. The net input voltage to the amplifier Vid, that is equal to Vin1 minus Vin2. The difference between the two input signals get amplified and appears across the output terminal. Now, the voltage gain of the differential amplifier is called the differential voltage gain. The differential voltage gain AD, the differential voltage gain is indicated as AD. AD is given by the formula V0 divided by Vin1 minus Vin2. Now, Vid is the input difference voltage, or it is the net input voltage to the amplifier. It is given by the formula Vin1 minus Vin2. Now, let us consider Vo is the output voltage of the amplifier. Now, the differential voltage gain is defined as the ratio of output voltage to the difference between the input voltages. That is, AD equal to V0 divided by Vin1 minus Vin2. Consider we are applying only one input. only one input is applied to the amplifier. When single input is applied, both transistors will amplify the signal and we are going to get twice amplified replica of the input signal. Now, when both input signals are applied, the amplifier will amplify the difference between the two input signals. The difference between the two input signals is amplified and appears across the output terminal. Now, the voltage gain of the differential amplifier is called the differential voltage gain. The differential voltage gain ED, it is given by the formula V naught divided by V in 1 minus V in 2. It is defined as the ratio of output voltage to the input difference voltage. V in 1 minus V in 2 can also be written as VID. It is the input difference voltage. Let us study the other modes of operation of the differential amplifier. One of the mode known as the common mode operation. In the case of the common mode operation, both input terminals of the differential amplifier are joined together and the input signal is applied to the common input terminal. Now, let us consider the common mode operation. When same input voltages are applied to both input terminals of the differential amplifier, the amplifier is said to be in common mode operation. You know, when same input voltages are acting simultaneously, the net input voltage to the amplifier becomes 0. Consider V in 1 and V in 2 are the inputs. When same input voltages are applied to both input terminals, then V in minus V in, the net input voltage to the amplifier becomes 0. Therefore, the output voltage also becomes 0. There is no electronic circuit that can reduce the noise voltage to 0. But with the help of this common mode circuit, it is possible to reject the noise voltage completely. One of the property of the common mode operation is that it rejects the common mode signals such as the noise voltages. These noise voltages appear across base to emitter terminals of both transistors and the resulting noise voltage reduces to 0. Now, the ability of the differential amplifier to reject the common mode signals such as the noise voltages is expressed by what is known as the common mode rejection ratio. The common mode rejection ratio is the ability of the differential amplifier to reject the common mode signals such as the noise voltages. Now, let us study the definition of common mode rejection ratio. The common mode rejection ratio is defined as the ratio of differential mode gain to the common mode gain. Now, the differential mode gain, already we have determined the differential mode gain. The differential mode gain is given by the formula V naught divided by V in 1 minus V in 2. It is defined as a ratio of output voltage to the input difference voltage. Now, the common mode gain can be calculated using the common mode configuration. A known voltage is applied to both input terminals of the amplifier and the output voltage is calculated. Now, common mode gain is given by the formula ACM equal to V naught divided by V in. So, therefore, common mode rejection ratio is defined as the ratio of differential mode gain to the common mode gain. The next mode, that is differential mode or the dual input mode, also called the double-ended input mode. In the case of the differential mode, two opposite polarity signals are applied to both input terminals of the amplifier. Two opposite polarity signals are applied to both input terminals of the amplifier. This operation is called differential mode operation or dual input mode, or it is also called the double ended input. Now, when both input signals are applied to the differential amplifier simultaneously, the amplifier amplifies the difference between the two input signals. So, it is called differential mode operation. Now, in this case, the differential mode gain is given by the formula AD, that is equal to V naught divided by V in 1 minus V in 2. It is defined as the ratio of output voltage to the input difference voltage. That is AD equal to V naught divided by VID, where VID is the input difference voltage. Next is the common mode rejection ratio. Already we have defined the common mode rejection ratio. The common mode rejection ratio is defined as the ratio of differential mode gain to the common mode gain. Very easy to calculate the differential mode gain. What you have to do? You have to apply input signals to both input terminals of the amplifier, and then the resulting output voltage is determined. So, now calculate common mode voltage gain. In order to calculate the common mode voltage gain, same input voltages are applied to both input terminals of the amplifier, and the resulting output voltage is determined. Now, voltage gain is nothing but ratio of output voltage to the input voltage, so that we can calculate ACM. So, now what is CMRR? CMRR equal to AD divided by ACM. It is defined as a ratio of differential mode gain to the common mode gain. The CMRR is often expressed in decibel. The CMRR in decibel is given by 20 log to the base 10 AD divided by ACM. You know what is AD? AD is the differential gain, ACM is the common mode gain. So, CMRR in decibel, that is equal to 20 log to the base 10 AD divided by ACM.